and we are happy to welcome Laura. So a little bit about her. So she is a professor in Dresden now, and she did her PhD in Brussels at ULB and a postdoc at Harvard, and another postdoc and a professorship in Vienna Technical University, after which she moved to Italy. So please, Laura.
Thank you very much. Yes, welcome everybody. So this is the second lecture in the series of 3 about this topic, which is called celestial holography. So I'm going to start by, thanks again to the organizers. I want to emphasize again, thanks for the initiative of putting together. I know it requires some effort and time to do that. So thanks again. I think everyone benefits from this kind of initiative. I'm going to start by a quick review of what we said last time. And again, as on Monday, I want to encourage you to interrupt, to make questions or comments, stop me, so that we are sure to be on the same page. I know some of you might have different training. So today will be a part, again, more based on amplitudes and / CFT, but more amplitude side. And then in the second part today, we are going to switch gears a bit and talk about gravity and asymptotic, make connection with the topic of asymptotic symmetries that Daniel introduced earlier, and see what it can teach us about celestial holography. So let me start by a review. So this is a slide which is meant to summarize a little bit the main idea behind celestial holography, which is the idea that it's possible to recast the S matrix. So here I'm working essentially in 4-dimensional spacetime. For 4-dimensional spacetime, it can be encoded in the celestial, what is called a celestial conformal field theory. So the word celestial, again, is there to emphasize 2 things. The first aspect is that it's supposed to be living on the 2-dimensional Euclidean sphere at infinity, which is called the celestial sphere. So it's the Riemann sphere, the projective null cone, CP1, you name it. This is what the celestial sphere is. And the word celestial is also there to emphasize the fact that it's still a yet to be understood and unknown theory. So we don't know yet to which extent it is a conventional CFT like the one we have in the yellow book here on the right. And I'm going to explain today, we will face unconventional features of this theory. And also very nice feature, namely a feature that resembles very much a 2D CFT that we know and love. And again, we know a lot of stuff about 2D CFT, and we have many techniques that have been developed for 2D CFT. So it might be a good thing to have. So how does this work? Let me try. I'm going to use the pointer again. But I never know where it is. It's in, let's see. It's not in the annotation. I don't know where this pointer is. Never mind. Otherwise, I can.
We can see the arrow.
You can see my mouse? Okay, then it's fine. Yeah. So how does this mapping or dictionaries you use in the spirit of holographic dictionary in EDS-CFT? So as I explained on Monday, we have the S matrix and we have incoming and outgoing particle, massive or massless, which come and exit out through the celestial sphere at a given point Z and Z bar. And by using this integral transform called the Mellin transform, we are going to recast those amplitudes in a new basis called the celestial or conformal basis, where now each particle in the bulk will be associated with an operator of conformal dimension delta, which is inserted at a given point Z and Z bar in the sphere. So again, the insertion of this operator is determined by the initial labels Z and Z bar towards which the massless particle is heading to. And the dimension, the conformal dimension, is imprinted, is the imprint of the energy of the particle. So this is the dictionary again, only for massless particles, which have p squared equals 0. And notice, however, I didn't present this, but there is another map for massive particles, so these particles which arrive here at time like infinity. It's a different integral transform, but it exists. And in other words, any scattering amplitudes you like might be recast by some objects of this form, which involve a bunch of operators, can be incoming or outgoing, which are labeled by the dimension, their spin. Here I haven't written the spin, but it has also a spin, and point Z and Z bar, okay? And the idea of this program, at least in its bottom-up version, so in principle, the idea is that if we had a complete flat space holography, we could, we wouldn't know, we would have examples of such theories from which we could infer new things we didn't already know from the bulk. But so far, most of the efforts and most of the results have been obtained from the left to the right, namely start with the amplitude, recast in the basis, and then interpret this as some correlation function of a 2D CFT and see what this CFT look like, which properties it has. Okay, so today we are going to see an example of such a map by working out an explicit amplitude and do the Mellin transform and rewrite this in the conformal basis for the simple example of a 4-point function, so a 2-to-2 scattering process of massless scalars. So before I start, is there any question on that, on what we saw last time? Okay, so if not, then let's start with this example. So we are in the constant of a 2-to-2 scattering, which I'm going to take my particle to be 4 massless scalars for simplicity, but you can do this with other spinning particles. So as explained many times, if you have a massless particle, you can label it by its energy and the point Z bar, which it crosses the sphere. And then okay, they can be incoming or outgoing, which explain this minus sign here. And an important object for a 2-to-2 scattering is the cross ratio. So this is a conformal invariant. So it's the ratio of Z13, Z24 with Z12, Z34. So Zij, remember that is the difference between Zi and Zj. Okay, so this is Z1 minus Z3 and so on and so forth. So this is an important quantity. And in the 2-to-2 scattering, we also have these building blocks, which are the Mandelstine's invariants, denoted by S, T, and U. So if you wish, S is the center of mass energy, T is related to the momentum transfer, and you have also this other Mandelstein invariant here, which is related to S and T when you're on shell. So here I've just rewritten them in terms of omega and Z here. With my conventions here, there are some conventions involved. And this is hopefully a consistent set of conventions. So we have momentum conservation. So the sum of p's are 0, which in terms of the Mandelstam invariant is expressing the fact that the sum of these 3 invariants is equal to 0. Okay, so you have only 2 independent Mandelstam invariants in the usual scale. So this is just basics about scattering amplitudes in a flat space, in momentum space. So for a generic amplitude in momentum space can be written as a piece, usually sometimes we strip out this piece, is the momentum conserving delta function, right, which imposes sum of pi is equals 0, times the more interesting part, which is I call curly m here, which is a function of, say, s and t, okay? So this is just saying momentum is conserved, and this contains the interesting part of the amplitude. It's very generic. So now this is how we usually write amplitude, this 4-point amplitude in momentum space. Now let's look at the celestial amplitude that I've been advertising on Monday. So how do you obtain the celestial amplitude? Well, the dictionary is pretty simple. You have 4 particles, so you will perform 4 Mellin transform, okay? One on omega 1, one on omega 2, 3, and 4. And then as a result, we are supposed to get something I call curly C to denote, to call it a celestial amplitude, so 4-point amplitude, which will depend now on the deltas. So as you're going to see, most of the technicalities and most of the computations involved in celestial holography have to do with, of course, this Mellin transform and how to do these integrals in a sort of a smart way. So there is a nice technique, a trick, if you wish, to do these integrals, which will have a nice property as you're going to see. So the trick is to do the following change of variables. So instead of working with the original omega i's, you're going to introduce omega here, whose squared is the center of mass related to the center of mass energy S. So there was the Mandelstam invariant that I introduced before. And you're going to introduce also the sigma i's, which are the original energy of your massless amplitude particles, sorry, divided by this omega for I equal to 3, 4. Okay, so again, let me stress that now this omega does not have any particle label, okay? This omega is not one of the omega of the particle, this omega is really essentially square root of S. So it's just a change of variables, but it's pretty useful as you're going to see. So in terms of these new variables now, the volume here integral is going to be written in terms of this. So there is a 2 here. This is just coming from the fact that, so you see this S is related to omega 1 like so. So the 2 is essentially coming from the fact that you have this squared here related omega and S, and just a very simple change of variables. And now one of, I should say, tedious exercise, but as you're going to see, once you have done it once, you don't have to worry about any longer in your life. So is to rewrite this 4 delta function, well, this delta function, momentum preserved delta function, in the following way in terms of these new variables. So it's very cumbersome expression, so bear with me, but let's check. So we started with 4 delta function. We better have 4 delta function on the right, and this we have 1 delta 2 3 4. Okay. Now notice that this delta function here, I'm going to come back on this later on, but involves the cross ratio. So remember, Zi are the points on the sphere, but Z is the cross ratio. Don't confuse the Z with the Zi, okay? So this is delta function of the cross ratio here, which will have an important implication later on. So once you have you can play around with these delta functions and these new variables, and now you can use this. So you see, we are going to make 4 integral over these sigma i's. So now you can perform, if you wish, you can absorb this delta function into the integral. And on the support of this delta function, what you can see, it's also a short exercise, is that the Mandelstam variable S, T, and U become given by S. Well, S was by definition. Now I call it omega. I introduce omega squared, which is exactly equal to S. And T simplifies a lot. So you start from the expression here on the top of the slide, and then massage it, and then you see that on the support of this delta function, T is just minus the cross ratio times omega squared, and then U is minus the sum of those. Okay, so this is a tedious exercise, but you know, at some point one has to compute these Mellin integrals, and this is doing the trick. So now we can, using this, so you see now you can do the integrals over the sigma i's, and the result you are going to get is the following thing. So let me first stress that you see I'm performing the three integrals here on the sigma i's. So these integrals will disappear, but there will remain this integral here over this omega over the center of mass. So this is the integral here that remains, the integral over omega. And now, as I told you, on the support of the delta function, S is by definition omega squared, and T becomes minus Z omega squared. And then I have split this integral. I splitted it from the thing that is boxed in red here, which is pure kinematics. Okay, so I have, this is what also this change of variable is implementing in a sort of nice way, is that this piece here doesn't depend on the detail of the amplitude you're looking at. So remember, you had this delta function, delta preserving delta function, this momentum preserving delta function in the momentum space time, all the dynamics or the interesting part of the amplitude, which is encoded by this curly M function, which depend on S and T. After doing the Mellin transform, what you get for the celestial amplitude is that all the interesting part of all the dynamics is encoded into this only one integral left, so to say, on this omega variable here. And you have to evaluate M at this value of the Mandelstam, okay? And all the rest is the kinematics takes the following form. So it doesn't depend on this variable omega, so I could pull it out of this, the omega integral. Okay, now notice that here I have introduced this beta. So beta is the sum minus one of the conformal dimension of each individual particle. Okay, so in other words, let me make a few comments. So this I have just rewritten the same stuff. I'm going to call this dynamical piece curly C, which depend on beta and the cross ratio. So some key remarks is that notice that I haven't assumed here in this computation is pretty universal, because we didn't assume anything on the detail or the theory you were working with. I just assumed that there were some massless scalars, but I didn't say in which theory they are. Even if this is computed perturbatively or non-perturbatively, this is valid regardless of that. And another interesting point to remark is that all the interesting piece in the celestial amplitude, the dynamical part, depends only on the sum of conformal dimensions through this variable beta. Okay, so unlike a usual CFT, which depends generally on delta 1, delta 2, delta 3, delta 4, here it will only depend on the sum of those, minus 4. Okay, so this is a first remark. A second remark is that I have worked here with scalars, but you might wonder, okay, what happens if I were to do look at the 4-point function of gravitons? Since we care about quantum gravity. Well, for gravitons, you will get exactly the same 4-point function, celestial 4-point function. The only thing that will change are these exponents here. You see this exponent here I'm circling. These exponents do depend on the helicity or the spin or the twist, you name it, of the particle. So if you don't have a scalar, these exponents will be different, but the form is the same. So this generic form still holds. And another point that I want to emphasize is that, as we can see, the 4-point function involves this delta function of the cross ratio here. And might not be totally obvious. Well, yes, in a sense, because the presence of this delta function was just coming from the momentum conservation. So in other words, the presence of these distributions is just a consequence of translation invariance in the bulk. And so in this sense, this is unavoidable. So the moral of the story is that you have a 4-point amplitude in the bulk, which is translation invariance. Once you do this Mellin transform, so once you go in the celestial basis, you will hit in your face this delta function here. And what this delta function here is saying geometrically, you can convince yourself of that in different ways, but what it's telling you geometrically is that so you have your celestial sphere. In principle, you could think, okay, I can insert all my particles at any points on the celestial sphere. What celestial CFT is telling you is that no, you cannot do that. You have to, this is what this delta function says, you have to insert your operator insertion on the circle. Why is it a circle? Well, there is one way to see that. Some intuition you can have is that if you know the following fact, it's just a kinematic fact that when you have a scattering of 4 massless particles, their spatial momentum must lie on a plane. And so when you think of this intersection of the plane with the celestial sphere, then you know that they have to lie on the circle. So it's essentially what this delta function is telling you. And you see, it's extremely weird. It's from the bulk point of view, it's extremely natural because it's translation invariance. But from a 2D CFT perspective, this signals a non-locality of the theory because it's a distribution, okay? So if you hand on this sort of 4-point function to a person doing CFT, he will tell you, okay, let me try to understand with you what the celestial CFT is and give me the 4-point function. Whatever theory, perturbative, non-perturbative, it will have this delta function. Then he will look at you with a very weird face because it doesn't look like a standard CFT. So if you have this feature is signaling is one of the signal that celestial CFT is one of the, if you wish, unconventional feature of this theory, the distributional aspect. Then I'm going to comment more on that of how you can still make sense of. There are still nice feature about that, but this is an important aspect about celestial CFT. So maybe I've been speaking without interruption, so maybe I should stop already a bit.
Are there any questions? I don't see questions from the audience.
Okay.
I think, yeah, we're okay.
Good. And then there was the last, sorry. Now I want to tell you a little bit more about this blue piece here by taking an example. a simple example to see that there is also some fundamental feature of celestial sea. We can learn from that by looking at the following example. Let's look at a gravitational scattering of 4 scalars. Okay, so have four massless scalar which interact through gravitational scattering, and I'm just going to focus on 3 levels for now. So for such a scattering process, this function here, which before was kept very generic, is given by G Newton divided by T, because I'm looking at the T channel in this example. Okay, so it has a pole in T, S squared plus TS, just a fact. Now, how do you have to do with the celestial amplitude? Well, as I said, once you've been through this mess of delta function, the kinematic pal is fully worked out. The only thing you have left to do is compute this integral over this variable omega. Okay, so you just take your amplitude, okay, and then you replace S and T by omega squared minus z omega squared. This is what you get. And now you have to do this integral, right? So you have to integral this 3-level amplitude. So what you are left with, sorry, I think there is an issue. There is a typo clearly. There should not be an omega square here. Clearly, I mean, this is a typo. The integral you are left with should be omega squared times omega beta minus 1. So it's omega times beta minus 1. Sorry about that. Forget about this omega squared here. So that's the amplitude. That's the only integral left you have to do. Now let's do a little change of variable and use the x variable instead of omega. And what you get is this integral. Well, clearly, this is not a convergent integral. This integral diverges, except when beta plus 2 is a pure imaginary number, but there is no reason to expect that the beta plus 2 has to be a purely imaginary number. So the upshot of all these things is that your celestial amplitude is just not well defined. I told you have to just to compute this Mel integral. Well, look, I cannot do it. It's just not well defined. It blows up. So the celestial amplitude does not exist. Why is that so? Well, it is so because somehow, you see, in celestial holography, we are doing this integral over all energy scales. We're integral over all omegas. So somehow, celestial amplitude always knows, in this case, it remembers that you are working with a non-UV complete theory, gravity. Here, your scalar we're exchanging a graviton. So celestial amplitude remembers, well, knows, probes, if you wish, the UV incompleteness of your theory. Okay, so it's...
sorry, I have a question here.
Yeah.
Maybe it's also related to the previous slide. You said that if I have some kind of particle or field that's a higher spin particle, that is going to enter through these deltas on the previous. Yeah, you showed it.
Right here, right. Yeah. So yeah, this if you have a spinning say gluon or higher spin field, is going to be encoded here in these powers.
Mm-hmm. Yeah. And now what you are showing us is this dynamical part on the next slide. So this is what you were calculating, and then there is a problem with that due to problems from GR, right? But if you're considering some kind of theory that does not have this problem, then does it still appear? Because it seems as if this problem is independent, but if you have some kind of higher spin theory, then the other part should compensate, or
Yeah, exactly. So what this thing is signaling you, this feature of this divergence. So again, there is a typo here. So what this divergence is signaling you is that celestial amplitudes are not, you don't expect them to be well defined for non-UV complete theories. Okay, this is just because of the fact that we integrated over all omega. So it's, if you wish, it's if you're, if you look at different here, I'm looking at the case where the amplitude is the one for the gravitational scaling of scalar. If you have other theories, which are UV, for instance, if you're a much better candidate would be a string theory amplitude, which is UV, which is well defined, right? And in this case, you won't have this issue. So I'm going to comment on that later on. Indeed, you might have from other theory, like 5 to the 3 or something, like you might have issue at the other part, in the IR part, you might have divergences coming from this. So it really depends on the theory you're looking at. Of course, some of them are well behaved in the UV, and those one will give you sensible celestial amplitudes. Those one will give you sensible celestial amplitude. But again, so it might be a bug of this thing that, but actually it's also it also forces you, if you wish, to work. So this celestial holography part is forcing you. You cannot separate the UV and the IR in a clean way. There is this mixing all the way, and it forces you to deal with it. Okay, well, you cannot just do a perturbative expansion and just go around this issue. So it's also nice because it forces you to deal with this from the beginning. Yeah, and okay,
Thanks.
you might think, yeah, sure, thanks. Yes, another question, yeah.
Laura, that's really great answer. Maybe a couple of slides before, you mentioned all the information about spin, helicity, everything goes into the exponent there, right? But you
Yeah.
also mentioned like twist. Did you mean something by twist, or you just
Oh,
meant
no,
like
sorry. I just mean the twist is another name for the in
spin,
CFT,
I guess.
for the difference between H and H bar. So yeah, which is called
Okay.
which is the 2D helicity. Yeah.
Okay, yeah, the helicity. Okay, thank you.
Yeah. Yeah, because sometimes people have their preferred names. There is no.
I know. I thought it may be translating from French or so, but
No. Yeah. Okay. So yeah, thanks a lot, Eva, for the question. It allows me to clarify a little bit what I mean. And then you might say, okay, maybe this is, but again, it's not going to cure, as I already announced, I already spoiled this, but you might think, okay, no, it's because you looked at tree level. If you were to add a finite number of loop correction, this might cure the issue. But actually, you can see it's not the case. I'm not going to explain all this, but essentially, if you work at any, so this is the amplitude at a finite number of loop, big L, then you can see that essentially this will translate into a finite sum of powers of omega and log omega, okay? With m and n are integer here. And then the integral you will get instead of the one above is this one. And essentially it's the same story, except if beta plus 2 plus m is purely imaginary, which again, there is no reason for this to happen. This is ill-defined. And even if beta plus 2 plus m is imaginary, then you can do this integral, but that you get a derivative of delta function. So, I mean, it's not much better. It's not much better behaved. Okay. So this is one of the key feature about celestial amplitude I wanted to emphasize, because as you see, it's very different from the usual. And in momentum space, we have a perturbative amplitudes, and it's perfectly well behaved, and we can work with that. In celestial holography, typically it forces you to have UV complete theory to have sensible amplitudes. modulo some other examples, of course. And I'm going to also comment how you can somehow circumvent this and still say something interesting for celestial holography.
Just a remark.
Yep.
Isn't this an artifact of the milling transform?
Yeah, absolutely.
There is something deep in there.
No. There is nothing super deep. It's just the fact that you're probing all energies from 0 to infinity at the same time. So of course you might expect some wild behavior, and this is what you get indeed. But it's nice to see it explicitly, and especially this computation. You see, it's particularly making the distinction between what is the kinematics with what is left with this integral over this variable omega. But yeah, it's just coming from that. You might have expected it.
In other terms, maybe it amplifies this UV character of the amplitudes, this milling transform. So
yeah, absolutely. As soon as you will have something not well defined around, this in doing this integral, you will hit this problem in the face, and yeah. Is there any other comment? Thank you. Okay. So again, I am planning for 1 hour, and then we can incorporate a question in between. So to as the lecture go, yeah.
Yeah, perfect. Yeah.
So yeah, good. So here is where we stand in the plan. So we just saw this example of 2-2-2 scattering, and we saw this UVIR mixing feature. Now I'm going to tell you about something which is a rather nice feature about celestial holography, which is the fact that you can have a notion of operator product expansion, which are very important in CFT, into this CFT also, in celestial holography. And then is going to connect with my last lecture, which has to do with this new development about this W1 plus infinity symmetries. So this will be directly connected to the celestial OPE of gravitons. So it will be also of use when for tomorrow. Okay, so let me remind you what is an OPE very quickly in a CFT. I mean, this is a very classical stuff in any CFT course. So essentially, an OPE is telling you that if you have two local operators in your CFT, okay, essentially the product of these two operators, when the points become close to each other, can be rewritten as a series of one involving one operator only at one point. Okay, so in general, this is quite of a complicated sum. Here is a schematic way of writing this OPE, but you really have to think of that this sum includes the descendants of this operator, so derivatives of them, of it, and higher spin as well. Okay, so in general, this is what this sum should be about. So you should also know what is the range of delta under which you are summing. And this coefficient here in this expansion give you what is called the OPE coefficients. And why is it so important in CFT? Well, because for a unitary local CFT, the following data are enough to reconstruct all correlators. So the following data are all these OPE coefficients together with the spectrum of primary operators, namely the knowledge of all the conformal dimension and spin. Okay, so if you know this, and if you know all the OPE coefficients, essentially you know the 3-point function, because the data of the OPE coefficient is the same as the coefficient of the 3-point function. And then you know the 4-point function, then you know the 5-point function, and you can reconstruct all correlators in your CFT. So that's why people in in the community, let's say in the conformal bootstrap, say that these are the CFT data, because once you know that, you know the theory. Essentially, you can solve the theory. Okay. So this is a really important, the OPE and the OPE coefficient is a key aspects about CFT. And we would like to see whether there are some notion of OPE in celestial holography. And as we are going to see now, the OPEs in celestial CFT are related to what is called the collinear limit of amplitudes. So what is a collinear limit? Well, a collinear limit, as the name strongly suggests, happens when you take a limit where two momenta, say pi and pj, become collinear, so parallel to each other. In other words, their product goes to zero. So remember that the product of, well, this is just a fact that you can check easily. The product of two massless momenta can always be written as omega I, omega j times zij, z bar ij. So you can see that the collinear limit can be implemented by zij going to zero. So let's see. So here we already see some collinear, well, some OPE limit appearing because zij is going to zero. So let me try to make that a little bit more fluffy. So in the collinear limit, you can always write pi plus pj as another null momentum. Okay, this is the so-called collinear momentum. Why is that? Well, because essentially just square this. Okay, you square pi plus pj, you will have pi squared, this is zero because it's massless, it's null, plus pj squared 0, and plus 2 pi dot pj, and pi dot pj is 0. So you can see that you can always rewrite it as some null momentum. And there is some nice properties of amplitudes when you take this collinear limit. So when you take pi and pj to be collinear to this, let's call it big P, okay? Then you are going to have a sort of factorization of your amplitude. It's a factorization because now it will involve the amplitude, but now you see, instead of having explicitly an amplitude depending on P1, Pi, Pj, and Pn, now it will just depend on Pi, this particle P, and Pn, okay? So it has only n minus 1 particle inside. And there is this splitting function here, it's called the collinear splitting function, whose expression, of course, depends on which theory you're working on. This is a very generic formula here. And the sum runs over the quantum numbers of the particle big P. And again, what are the quantum numbers of this particle P depend on which kind of, what are the particles you take collinear in the first place, okay? So this is a very generic expression. However, just know that in the amplitude, people have been studying a lot collinear limits of amplitude, and there are some nice features, some sort of universal feature. So universal meaning that, yeah, it doesn't so much depend on well, it just depends on the moment and so on. And somehow this collinear splitting function is protected against that's what I meant, against loop correction. Okay. And we say that an amplitude has a collinear singularity. Well, is if the splitting function has some singularity in this collinear limit when you send pi parallel to pj. Okay. So if it's the first time you see this, don't worry. If you've been working with amplitudes, this is something you know very well. So let's do an example just to give you an idea of how we can see the OPE behavior here. So let's look at two gravitons let's take an amplitude and imagine that two gravitons inside I'm going to take them of both of them of helicity plus become collinear. Okay. Then okay, people have worked this out. Again, this is a very amplitude result, so I'm not going to derive this, but the splitting function in this case, so here it means that the particle I, which has helicity plus, and the particle J, which has helicity plus and represent a graviton in my example, become collinear with the particle P, big P, the collinear momentum, which has to be of helicity plus. Again, this is a kinematic fact of life. This has to be helicity plus, cannot be helicity minus. And the splitting function takes this form, where I've introduced this omega p, which is the sum of omega I and omega j. Okay, so this is just what the result is of this splitting collinear function in this specific example. Again, here this is in momentum space. Now the goal is to see what it gives for celestial CFT. Is there any question about the story of collinear limit or OPE or both? So a priori, these two things, so celestial holography is connecting these two things, will connect these two things together. Okay, so
I didn't
here
see any questions from the audience, but I was wondering, does it become much more complicated when you include both helicities?
So again, Eva?
Does it become much more complicated when you include both helicities?
No. So if you have a plus and a minus, then you can have you have also something. If you have two plus, that's the only one, but you have a plus and a minus, you have another expression here which is not much more complicated. Yeah.
Okay, thanks.
Yeah. But what as you're going to see tomorrow, I will especially care about the all plus or all minus helicity sector for this W infinity reason. But no, at the level of this splitting function and what I'm going to say, you could also do it with a plus and a minus. Yeah. In fact, in the original paper, I'm going to list at the end. On top of the reviews, I'm going to give more specific references for where I took this computation so that you can find, well, in the paper where they have done that, they also give the expression for plus and minus. Okay. Okay, let's go. Okay, so let's do it. Yeah. Sorry, I forgot to say something. So I said before, we have a collinear singularity if the splitting function has a singularity. So here, let me make an important remark, is that you will often hear, if you're in the amplitude community, you will hear people say that GR doesn't have collinear singularity. And this is true for real momenta. So for real momenta, what you can see is that for real momenta, what you can see is that so if Zij goes to 0, so you might think, okay, when Zij goes to 0, I have a singularity here. But for real momenta, it also means that Z bar, so Z bar will be the complex conjugate, right, if it's real, of Zij. So it will go to, I mean, this would not be singular. However, we are going to work now in complexifying momenta, and this is going to be important for a reason we are going to see. When you complexify momenta, then what you can do, you can take the so-called holomorphic linear limit, where you send Zij to 0, while keeping Z bar ij fixed. This is something you can do when you complexify everything. And just to tell you, people in amplitude, they complexify the momenta all the time. And there are many things interesting that you can do in complexify momenta. This is something very standard, just for you to know. And for the case of OPE, it's going to play an important role. Okay. So because precisely this holomorphic limit is going to allow us to extract some OPE coefficient. Okay, so I have just rewritten here the splitting function here, and let's see what it does for celestial amplitudes. So again, what do you do in celestial holography? You do Mellin transform. Okay, here you have as many of particles of Mellin transform that you should do. But here, let me focus on the interesting Mellin transform, which are the one for the particles I and j that you take collinear. Okay, so let me focus on the Mellin transform on these particles I and j. So you have to make two Mellin transform of this splitting function. Again, turns out nice to make this change of variables, where you introduce this t, which go from 0 to 1, just as change of variable. And you can see that I am introducing t, but I still have that omega p still the sum of omega I plus omega j, okay? And in terms of this new variable, you can rewrite this integral as follows. So you have an integral over omega big P here with this power times this integral over t. And now if you're familiar with this integral you immediately recognize as being the integral representation of the Euler beta function. Okay, so this is the Euler beta function in terms of gamma function, but it also admits this integral representation. And this is the Euler beta function of delta I minus 1, delta j minus 1. So great, this was a very easy integral to do at the end. And from that, we obtain the following thing. So we have a celestial amplitudes of n particle. Among them, I and j are taken to be collinear in a holomorphic way. So zeta j is sent to 0. What this little computation is telling you is that in this limit, so modulo terms of higher order, this amplitude factorizes as this beta function here, this Euler beta function, times, what is this? Well, together with the other Mellin integral, this reproduces for you the celestial amplitude. This is just a definition, if you remember, of the celestial amplitude, but now involving one less particle. Instead of I and j, it involves the particle p, and as you can see, so it has conformal, in the Mellin it's just delta minus 1. Here it means that it's the celestial amplitude of involving delta I plus delta j as conformal dimension. Okay. Let me know if there is something not clear about that, but essentially that's the computation.
Just a comment on this formula. Is this due to the fact that these two particles will hit the celestial sphere on the same point, this reduction? So we don't need to know both.
Yeah, exactly. So this is, are we going just to see next? This is exactly, it implies an OPE coefficient, because in this you have your celestial sphere with many insertion and different points, and now you're taking two of these points to be very close to each other. Okay, and this is what is going to give you as we see, is a new amplitude, new celestial amplitude with one insertion less. And it's exactly a statement of an OPE. Okay. So indeed, as I just said, here I have rewritten the OPE expansion. What you have just seen is this formula. I just rewritten. I have not done anything here. And so don't look at the last line for now. I'm going to explain. But so this is the expression in terms of amplitudes. So if you interpret again as celestial holography, we would do your amplitude as correlation function of operators, each of certain dimension. This implies that the following OPE, right? Because you have, okay, I should have called this delta 1 and 2 I and j to be very consistent, because it's the one that I said would become collinear, but here I have renamed it in 1 and 2, so bear with me. So, but essentially this is what it's telling you, is that the insertion of these two operators, when they come very close to each other on the celestial sphere, well, it's the same as inserting a single operators, O, but now of dimension delta 1 plus delta 2, because of this thing in blue here. Okay, and the plus 2 just mean that, as Eva asked about, these are here, I'm just writing the OPE of two gravitons, so they have spin 2 of positive helicity, so plus 2 plus 2. And this produce another graviton of positive helicity, again, because the collinear momentum had to be of, the collinear particle had to be of helicity plus as well. And we see that we have a singularity here at Z12, so it really takes the form of some of an OPE. And okay, I've been a little bit sketchy about this, about keeping track of descendants here in this derivation. But if you are very, very careful, you also have, you actually should have a sum of over all descendants here. So the first line that we saw together is n equals 0 in this thing. But if you include as well descendants, this is the formula that you're going to get. So that's the final expression. So what we have done together is that we have seen how a collinear limit in the bulk, in the case of massless particle here, gives rise to a formula, which is exactly the formula you can have when you look at the operator product expansion of a 2D CFT. Okay? And the OPE coefficient here is fixed. You see, we have computed, by the way, this OPE coefficient here. It's fixed to be this Euler beta function. And we have taken a holomorphic limit where Z12 goes to 0, and we have this singular, well, this typical pole as in the usual OPE. And then, of course, there are some more terms, more regular terms that I am not writing in this expansion. Okay. Let me say something extra, is that here we have gone the sort of long, more painful road, even though it was, come on, it's not that painful, but there is another way to derive this OPE and see that the OPE coefficient is a beta function. It's by imposing symmetries. So you start from a generic expression for an OPE form, and then you impose the asymptotic symmetries, which I'm going to turn on next. You say that it should be consistent with the existence of asymptotic symmetries of flat space, and then you can also derive these OPE coefficient from a pure symmetric point of view, symmetry-based point of view. But I'm not going to derive this now because I haven't talked about asymptotic symmetries yet, so it would be a little bit confusing at this stage.
Does this relate to the soft theorem?
So
because
the
we have
soft
the
theorem.
pole. We have the
Sorry?
pole at. We have this pole. It resembles the soft theorem.
So the soft theorem is another interesting factorization of amplitude, which arises when you take a small energy, so omega goes to 0 limit. I'm going to talk about that probably tomorrow. I'm not sure how much, but it's yet another thing, and this is related to the presence of asymptotic symmetries. But it's yet another thing. So in In amplitudes, there are many interesting formula you can get. So this collinear limit factorization property is one, but you also have, as you said, the soft limit, and the amplitude also give you a factorization. However, the soft limit doesn't give you an OPE, okay? It's really the collinear limit that you can map to an OPE from the CCFT, celestial CFT point of view. Soft theorem tell you other thing. They give you current algebra for celestial CFT, and I'm going to talk about that tomorrow. Okay, so let's see. It's already 5. Are there more comment or question about this computation, so to say, of the spirit of that?
Well, I have a question, but I don't know whether it's a little bit early to ask it because you say you didn't talk about the synthetic symmetries yet. I was wondering, can I see already connection with Carroll series? Carroll?
With what?
If I can see already connection with Carroll series?
Chiral.
Or is it too early? No, Carroll.
Chiral or Carol? C-H-I-R-A.
Actually, now I wonder about the both, but the initial question was C-A.
Okay, Carol, like Alice in Wonderland.
Exactly.
So, okay, so Carolian holography, it's a different approach to flat space holography. And so in particular, to recast amplitude, what you can do is you can recast amplitudes in terms of Carolian correlator, but the map is not this Mellin transform map. So there is, it's very different. The notion, for instance, the notion of OPE, whether it even exists or makes sense in a Carolian CFT, is very different than this one. This one is very akin to the usual notion of OPE in a 2D CFT, where everything resembles, you see in this picture of Celestial versus Carolian, everything resembles more to a CFT. But the price to pay is that the CFT that you arrive at seems to be strange. In the Carolian picture, it doesn't look like a CFT at all. So you avoid some issues, but it's also unclear what is the field theory defined on the null manifold at the quantum level. It's hard to make sense of. So it has different drawbacks and also different advantages. But at each step is interesting to see whether, you know, one part, one of the aspects is more interesting to it than the other. So yeah, it sheds, both of them shed light on different aspects of the. At the end, you see, there should be only one theory. I mean, you can express it in different ways, but which one is the more promising way of getting insight into is taste dependent, I would say, at this stage.
Okay.
So maybe it depends on the data that is recorded and where it is recorded. Is it recorded on the celestial sphere or on the whole boundary?
Well,
Maybe
both. Both. You know, I mean, you know, it's just a matter of. It's everywhere at the same time. Everywhere, everything all at once, right? It's just the way in which term you want to phrase your dual theory. Do you want to think of it? Do you think if it's a better idea to look for a 2D CFT because for some reason you know a lot about CFT techniques? For instance, here in this case, OPEs, you know, OPE in celestial CFT, in usual 2D CFT are extremely well known, well understood. You can infer new things that you could hope that thanks to this structure that I'm scratching the surface of this OPE, you can gain new thing on the bulk side? Or do you think maybe it's not natural to repackage everything on the sphere because you get this Mellin transform is integrating over all energies, and and you think it might be more promising to do a different way, this is I think the question this is still an open. I think none of the approaches have managed so far to give a fully fledged example of holographic duality for realistic theory in the bulk. So it's still an open question. It might be even you could come up with another crazy idea. I mean, this is maybe not even the end of the story. But the data is there. It's just a matter of how do you want to think about your boundary theory to be encoded, to be living? How do you want to formulate it? Hope that answers the question.
Can we see that that the celestial holography is an integrated Carolian? You integrated Carolian.
Yeah, absolutely. So you can make the explicit map between these operators here and would-be Carolian operators, and it's just a transform. It's just essentially a Fourier transform. It's just a Fourier transform together with the Mellin transform, and you can relate everything. We did that in some paper because there was indeed some confusion in the field about these two different perspectives, and people had in mind that they were incompatible to some extent, but they are they capture the same physics in the bulk, so they should be compatible with each other. It's just a matter of mapping. And as you say, what happens is that you take your Carolian field at the given retarded time, and then you integrate over this U variable, and then you get a celestial operator. There are many ways to see that. It's just also from the representation theory point of view. It depends really how you branch your representation into the Lorentz representation or into the representation intrinsic at null infinity. Good. So please continue asking questions. It's great. I think what I'm going to do, since it's already 10 past. I think I'm going to make a sort of summary of features that we have seen so far, and then I'm going to totally switch gear and talk about asymptotic symmetries and gravity. So in case you haven't followed anything about the lecture so far, you can recouple tomorrow. This will be largely independent, even though I'm going to make connection. So okay, so far what I've told you is that okay, you recast everything on the celestial sphere. You might question why it's a good idea, but okay, I was asked to talk about celestial holography, so this is what celestialography is about. And what we have seen together is that the collinear in the bulk gives you a 2D OPE in celestial CFT. So this is nice. This is actually a nice feature. We've seen also that intrinsically, because of the Mellin transform, there is a UV-IR mixing. This leads to inherent divergences of celestial amplitude or distributional at times, often, especially for low point amplitudes. However, there is a better behavior. You might consider, as I already mentioned, looking at celestial amplitude in string theory, which are UV well-behaved. There is also some work turning on the background field. I'm not going to talk about that so much. And again, as we saw that this divergent integral appear when you work at a finite number of loop in the expansion. So they appear that anytime you work at perturbative level at a finite order. However, if you go beyond that, so if you don't work perturbatively, then you avoid these issues. And people have been advocating that a good framework is to work in this iconal approximation, where you can do you can define celestial amplitudes which are much better behaved. And finally, and the summary of all this is that we are very far from having a well-defined definition or even axiomatic or a list of properties of what a celestial CFT should be. As I said, there are many unconventional features about this theory, which make them hard, for instance, to bootstrap, like in the community of the conformal bootstrap like to do. You see, in this case of celestial CFT, we don't know what really the spectrum is, the spectrum of operator, because we don't really understand what is the minimal set of deltas that we need to take into account. Clearly, taking any complex delta is too much. So we better understand what is exactly the minimal spectrum we need to describe this theory. These are open questions at the moment. And finally, the thing I want to emphasize tomorrow in the last lecture is that nevertheless, we can extract some universal behavior of this theory. And it's also true for Caroline holography, thanks to the symmetry algebra, and the asymptotic symmetry, which are going to give us current and current algebra for the putative theory. And these are universal, and they should be there, at least if you think that the symmetries exist as people think they do exist. So this is going to give a stringent constraint and interesting viewpoint on celestial holography, and is going to connect more about gravity and asymptotically flat spacetime. So this is what I'm going to do tomorrow. I don't think it makes sense that I start this part yet, because we were totally going to change gears, so to say. So yeah, I think I'm going to stop here for today, and then tomorrow we'll dive into the last part, which is this current algebra. So thank you very much for listening, and again, I'm still happy to answer a question.
Thank you, Laura, for a very nice lecture. Do we have some questions? There are already quite a number of questions, but do we have some further ones? There are many thank yous. I didn't see questions. Maybe when we are waiting, you also mentioned the chiral when I was asking about chiral. So can you also answer about chiral?
Well, yeah, no, I thought somehow you meant Carol, because Chiral, CHIRAL, because of the fact that I was taking this holomorphic or anti-holomorphic limit, and that gives me some chiral OPE, but that's all about the confusion. There is nothing more that I wanted to say about that, but yeah. So I understood that, yeah, I think Daniel already talked a bit about asymptotic symmetries. However, if I understand well, correct me if I'm wrong, but he hasn't touched so much into the 4 decays and maybe super rotation, which are specific to 4D. So is it correct?
That is correct. He focused mostly on the lower dimensions. So he covered in the first lecture, he talked about the chiral theories, then asymptotic symmetries in the second lecture. And then today he connected these two on the number of examples in which they checked explicitly both sides of asymptotically flat spacetimes, quantities, observables, and from the chiral. Well, which at that time they didn't call a chiral yet. And there is a question. So could you elaborate on the need to complexify the Cij in the collinear limit? I would assume that Z and overline Z are independent.
Zij.
Sorry, Zij, not Cij.
Right. Yeah, so you see, if you work with sorry, I'm going to hide this chat, otherwise I don't see my slide. Oops. So yeah, I mean, you see, of course, if you work with the real momentum as the normal person would start their life thinking about, then your z this stereographic coordinate zij should be the complex conjugate of z bar, not the other way around. So if you send one to 0, the other one goes to 0. So that's the reason why for real momenta, gravity is known to have no collinear singularity. Now, the question is why do we want to look at complexified momenta? First, again, let me just maybe say something that it might be not so well known, is that it's something that people do all the time in the amplitudes, because it allows you to discuss analytic properties of amplitudes. So the study of analyticity in the complex plane of amplitude is extremely important and powerful. So it traces back to a lot of old works. But in this specific context, the reason why it seems a good idea is precisely because it allows us to extract these OPE coefficients. So again, you see in the CFT, from the point of view of a CFT, having a sort of having this holomorphic singularity in the OPE is extremely natural. Like think of for instance the OPE of a stress tensor in a 2D CFT. It has this 1 over Zij to the power 2 or to the power 4 and so on. So it's a very natural thing to have from a 2D CFT perspective, and this can only be seen by going to complexified momenta. And this is the reason why in this context is particularly a good idea. And the second part of the answer is that we're going to see why these OPE that come from this holomorphic or anti-holomorphic. Of course, you could do everything for the anti-holomorphic, right? Set Z bar ij to 0 while keeping Zij fixed. I didn't say it, but of course you could do it as well. Is going to give us, is going to point out to a new symmetry for amplitude that was totally new, at least at the level of the S matrix. And this is the called W1 plus infinity algebra. And it's fair to say that without celestial holography or without celestial CFT, we would not have encountered this symmetry of amplitudes. And okay, the hope is that this tower of new symmetries do constrain the S matrix in a non-trivial way, and again, it's thanks to this OPE point of view, if you wish, that they were uncovered. I hope that answered the question.
I don't know.
Thank
Can
you,
you hear
Laura.
me now?
Yeah, I can hear you.
Okay, perfect. Thanks a lot. Maybe I misunderstood this coordinates Z and Z bar, because I thought they would be something like two real coordinates. So I thought they would be something like a base change from okay, so I imagine the sphere to be dependent on two angles. So I can either parameterize it by two angles or by these coordinates Z and Z bar. And this is why I thought I can turn one to 0 while keeping the other one not going to 0.
Okay. No. So in my convention here, Z and Z bar are complex coordinates. So they are the stereographic coordinates when of the usual Riemann sphere, so to say. So Z and Z bar are really, I gave the formula some time ago with cotangent theta over 2 times exponential of I phi in terms of the usual I and theta coordinates. So they are complex coordinates, which are, for real momenta, they are conjugate to each other.
Okay.
However, what you can do, you see, when people in amplitude work with complexify. You can complexify your momenta. And once you have complex momenta, you can also look at real and independent Zij and Z bar j as you were saying. So these amounts to work in a different signature, which is the so-called Klein signature of plus plus minus minus signature. Instead of working with Minkowski signature, that's what I mean, minus plus plus plus, you work with plus plus minus minus. So you work in what is called a split signature. In this case, you're not working with the celestial sphere, but rather with the celestial torus, because you have two real directions, so to say. It's something you can do. It's an interesting thing to do. It has also been looked at carefully in the celestial literature. But here it's not really what I wanted to emphasize on. But once you work in complexify, that's the nice thing about complexifying everything. You work in you complexify everything, and then at the end of the day, you can impose reality condition on your momenta, and then you can go either to usual mean signature or to the split or Kleinian signature. And people have studied that a lot in the amplitude. And in fact, for some amplitudes, it's only by going to complexify momenta that you find non-zero answers. For instance, at 3 point, a 3-point function of say 3 graviton is only non-zero if you go into either split signature or more generally into complexified signature.
Okay, thanks.
Yeah.
We have further questions in the chat. Should we focus only on delta equals 1 plus I infinity, or are there no restrictions?
So it doesn't seem to have to do a lot with having a full theory of quantum gravity. So just to be clear on this point, I'm not claiming that celestial holography is going to provide a theory of everything for quantum gravity in flat spacetime. Just one huge disclaimer here, right? It's a program that attempts to give a holographic description of flat spacetime, but I'm not claiming that this is the case. And it diverges again, indeed, because we were working, it was expressing, remembering the fact that we were working with a non-UV complete theory in the case I was giving, in the case I was saying. I'm sorry, I'm just reading slowly the different part of the question.
Sorry, I was reading the question above by Stefan Gallen.
Sorry,
you see? I was reading the above question and you focused on the...
Sorry, I skipped totally Stefan's question. Sorry, let me finish with the question of Sophie and then I will go back up. Sorry. And then Sophie's point is that for quantum gravity. Yeah, exactly. So I think I'm going to comment on that also at the end of the lecture, but one of the advantages, as we are going to see, these approaches has allowed us to find new organizing principle for a subsector of quantum gravity, the so-called self-dual, well, some sort of self-dual sector. I'm going to comment on that later, but it does have led to some successes. Of course, this is not the end of the story. I mean, it requires a lot of things to claim that, you know, this is not at this stage, as I say again, providing a full hologram of the full laws of quantum gravity in asymptotically flat. So, you know, people are trying to their best in this direction, and it has been useful. Even if you, I'm going to, maybe I can tell you my own perspective on that, is that even if at the end of the day, this program doesn't reach its pipe dream, namely provide a full holographic duality, along the way, so with this perspective or the Carolean perspective, you name it, along the way, it makes us to ask fundamental questions about quantum gravity, even classical gravity for what it matters, and about the infrared structure of gravity. For instance, now we understand that there are many things that have been overlooked, many symmetries, many observables, memory effects for gravitational wave. There has been a tremendous amount of efforts trying to find, well, that has allowed us to increase our knowledge about fundamental question in high energy theoretical physics, or even classical GR. You see, because all the story I'm talking about also connects with people working in classical aspects of GR on stability theorem, about Minkowski space, about black holes. There is a ton of exchange. And I think that's the most interesting aspect of this program, but this is my opinion, is that precisely it makes contact with many, many fields together. Amplitude, CFT, GR, you know, gravitational wave observables. And at the end of the day, you know, if we really want to solve important questions in quantum gravity, we will have to rely on the interplay of these things. I don't think it will be given by a small corner of a small amount of people. I think it will come from integrating all the insight from all the things we know in order to answer such huge question that we are left and we have to deal with in the field. Well, that's at least what I think. Then